bridge to the people.
Det er 2 gange den bord har været med i år. Det der.
Actually, these are the actual footage, so this happened in reality in 1940.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge.
Fuldstændig en ting sammen.
Det er nok kørt.
Only 35 mile an hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
So you can see this is very good example. Yes?
Can I guess, is that unstable?
Of course it's unstable. Of course, if it was stable, why they had this crash? But you know, this was in 1940, and I think $6 million for at the time was a huge amount of money. But they lost everything, as you could see, because the bridge was not stable, and the amount of wind they had, I think, was nothing compared to Denmark. So let's imagine how good was the design. But after this failure, the researchers used this bridge to develop a lot of theories and algorithms for civil engineering and mechanical part, and also for stability, stable theories, and so on. But that's why I'm saying that it's important to have a stable system, and we should always look at how the output will look like. Now I have some slides from another course which I teach on the stability. And again, here we use the same concept of using the poles for checking the stability. Here is one example with the plot of the output. So here I have this as a transfer function. And here, as you can see, I have one pole at -2, which is a real negative. So it is in a left side of the plane. It's somewhere here. So I have to have the stable system. If I do the plot, this is how the output will look like. And as you can see, as time goes toward infinity, 20 and afterwards, we have very stable line or output. So this is stable system. Another example I have here is this one, this transfer function. So if you find the poles, we have 2 poles which are complex numbers, but still the real part is in the left side, so it still is a stable. And as you can see, the output oscillates first, of course, but after a while, maybe after 5 seconds, 6 seconds, it becomes totally stable. I have another example, which is this one, which we talked about it before the break. So we have 2 poles which are imaginary, -j and +j. And if you do the plot of the output, you can see it oscillates forever. You can see the output is still bounded between -1 and +1, but it is oscillate forever. And that's why we call it marginally stable. We don't have this stable line at the end, at time goes to 0, but it still is marginally stable. And the last one, or next one, this is a totally unstable. Why? Because we have poles, 2 complex numbers. The real part is positive, so it is in the right side. And if you do the plot, actually this is still 20, but if you do the plot for 100 or 1000 seconds, you can see the output grow rapidly. So it oscillates and also grow forever. So this is totally unstable system. So that's what we talk about the stable or unstable. We always look at the output. And if you do or study the control engineering later on, you will learn that how you can design a controller to change this totally unstable system to a stable system. But it's for another course. Yes?
When we're talking about stable and unstable, can we talk about if it's longer, minus on the realdel, it's more unstable, and likewise could we talk about it's more stable if it's larger?
If we move this side, so you're saying that if we move from here to here, it becomes more unstable?
Yeah, I'm asking.
If we move from here to here, it becomes more stable?
Yeah, I'm asking if
No,
it's...
we cannot conclude
Can we
such a thing,
okay.
no. No, we don't have such a theory
It's
yet.
just stable or unstable?
Yeah.
Alright.
Yeah. We cannot identify how much is a stable or unstable.
Alright.
Yeah, just if it is or if it's not. Any question for stability? Okay, we don't need this anymore. Yes?
So it doesn't, as long as the system goes towards less oscillation, it is a stable
It's
system.
marginally stable. If it oscillates forever, it's
Yeah.
marginally stable.
Yeah, but if it goes towards less oscillation, because it could be,
It can go toward a less oscillation, but again, it stays in a bound. So I mean, I know what you mean. For instance, here we have this, and then maybe it becomes something like this, and of course goes forever.
Yeah.
Still, it oscillates. It becomes smaller or bigger, but again, it is under, bounded on some specific values. It doesn't
So it
grow.
doesn't
or,
go to infinity
yeah.
at some point.
Yeah.
Yeah.
Then it's marginal again. Marginally stable.
All right.
Okay. Any other question? Okay, now let's talk about convolution of two functions. Let's look at the unit step function again for now. So we are in board number 5. The unit step function, as you are familiar with it, has a value of 0 here and 1 here. Actually, for functions like unit step function, which has some value on a positive range of t, we call them causal function or signal. So this is a very good example of causal signal or function. So let's have cosine signal, for instance. If I do the cosine plot, of course, we have in both positive and negative range of t. So cosine itself is not causal signal or function. However, if you multiply this cosine with unit step, what will happen? This part will become 0, and then we have the part which is only for. So in reality, in actual world, all the systems and signals are causal because they operate in a positive range of t. But when we study mathematics, we have both negative time and positive time. And that's why I'm saying that the cosine itself is not causal, but if you multiply cosine or any other function which is in both, which has value for both sides with unit step, it will become causal. Now let's assume we have a two function, f and g, and we want to define or compute the convolution of these two functions. Actually, convolution is a mathematical operation which we implement to two functions, and it will generate new function. So again, from mathematical perspective, we have two signals f and g, and this is the notation we use to obtain the convolution. This f star of g in in t. This is f convolve of g of t. This is the formula we have for it. We have the integration of minus infinity to plus infinity of f of tau, which f is one of your signal you have. Then g of t minus tau d tau. This is the general formula for convolution. And the Danish word for convolution is folding. So if in any exercises or exam, which are all in Danish, you see folding, it's the same as convolution. So this is the mathematic equation. But as I said, in real world, we don't have f and g, which operates in both negative time and positive time. So now I will assume I have f and g, which both of them are causal. So I multiply both with unit step, and they become causal signal. If we do that, what will happen? Here we have f of tau, g of t minus tau. I replace it with the causal format of those, because I said that f is causal, so I replace f with this one. And also g is also now causal, so I multiply by this. Now I group them differently, and now look at how they look like. Just a second. I will back to it as again in a second. For now, I want to look at u of tau times u of t minus tau. And let's plot it and see what does it look like. What if I want to plot u of tau, how it is to look like? Let me check something on my notes, because I want to make sure that everything I plot is correct. Not this one. Just a second. Now I have a tau in x-axis. What is u of tau? It's a unit step, so if I want to plot it, this is u of tau. I do it with the, and this is one. Now I want to plot another function, which is, I do it with orange. I want to plot u of tau minus t. So it is the same with t unit shifting to the right. So this orange one is u of tau minus t. Okay. Another thing which I want to show, and it's important to know, if I want to plot u of minus tau, how it will look like? Any idea? U of tau is this purple one. And now I want to do u of minus tau. Yes? Exactly. Because let's see why it is another way. If we know that u of tau, based on definition, is 1 for tau greater than 0 and 0 elsewhere. Now when I want to plot u of minus tau, so it means that I multiply everything with a minus, of course. So then it will become 1 when we are here. Let's use another color, like maybe green. So this green one now is u of, or let's do green. So u of minus tau. It is the green one. Does it make sense for everyone? Okay, now another color, maybe pink. Here I need to multiply by u of t minus tau, but here I have the reverse. So what I need to do now, I will plot u of minus, I make the factorization of minus here. So t plus t minus. Are we agree with it? Because if I multiply this inside the parenthesis, I get this one. So, any idea of how minus t minus tau will look like? Yes, please.
Yeah, I'm guessing it will be 1 until minus t.
Minus t?
Yeah, so on
You
the
mean
left.
it will be 1 here?
Yeah, until minus t.
You mean
No.
here?
No, I didn't mean that, but that seems like a good idea.
I don't know. Just let me see what he says, and then I back to you. Yes.
The same as the orange one.
So you are saying that the plot should be the same as this one.
No.
Exactly. Why? Because when you multiply this minus inside this, you get exactly orange one. That's good. But here, I want to have this one. What is the difference between this and this one? I mean the white I have here, this white expression and pink expression. Yes, please.
It's the exact opposite of
Yeah, it's like what we did for u of tau and u of minus tau. They became the, not reverse, but opposite of each other. Here, this one and this one. So if I want to plot the white one now, with the white color, yeah, it should be here. The white one here and here. I try to make it a bold here. I hope that you can follow what I'm doing here. But now I have the white one, which is u of t minus tau. Also, I have a u of tau here. So I can obtain the multiplication for different range. Yes, please.
Shouldn't the white one and shouldn't the white one t should be t minus? Shouldn't be t minus. Should start on the other side, I think. The white one shouldn't start on the other side.
Here?
Yeah, it start over there, yeah. The function, the that one.
But if I understand you, it starts here and goes till here. Am I right?
No, it starts over there and goes to
Minus t.
minus t.
I don't think so. Let me double check. No, this one is correct. But let's do it again to make sure that we did everything correctly and everyone can follow. So I did a different plot now. So this is tau axis. And now this time I only do the plot of u of tau. So this is u of tau, which is the pink one. And we agreed that if I do the plot of reverse, so 1 is here and 0 here, it will become u of minus tau. Are you all agree with that?
Yes.
So if when you multiply whatever you have in the parenthesis with the minus, then you have to mirror it with respect to this point, for instance, we have here. Now, again, we did a plot for u of tau minus t, so t is here. So it is with the t unit shifting, so the green here and here. And this is u of tau minus t. And you know, the axis here now, if I do the dash line, we have this dash line here. Okay? The white one, which I want to have, is u of t minus tau, which if I multiply what I have here with the minus, then I have the plus. So what I need to do, if I mirror this with respect to this axis I have, then the white one would be u of t minus tau. So we do the mirroring with respect to this point, not minus t. Is it clear? I mean, this one is exactly the same as what we had above. Yes, please.
The only thing that confuses me is that t also changes from minus to plus. That's why I thought t should start on the other side. You know what I mean? Because you have
I know what you mean. You are saying that because we multiply this with the minus, then of course this t becomes plus t.
Yeah.
So, but you can see it is plus t, but also this one is also a minus here. And again, based on the same principle of u of tau and u of minus tau, the only mirroring happening here. We don't, actually in the plot, this t still is the same as what we had in the first place. But the only mirroring is happening is here. I know it's maybe a little bit confusing, but I don't know. Should I repeat it one more time? If you want, please let me know. I can do it. That's not a problem.
I'm just this tau variable is that is
Let's assume or rename the axis from t to tau. It's just a new variable name.
okay.
Because you know, when you do the plot in x-axis, you can have time, you can have frequency, you can have any other variable. And for now, we just call it tau.
Okay.
Okay. Should I go ahead or more question here? Okay, now. So now I want to find the multiplication of u of tau with this u of t minus tau. First, we will consider it if tau is smaller than 0. If tau is smaller than 0, we are in this range. U of tau, which is the purple one, is 0 multiplied by u of t minus tau, which is 1, which is 0. So this is multiplication. I don't know how should I write it, but this is multiplication. Not the comma or decimal point. Or maybe I can do this one. It's easier to understand, I think. Okay. Now, if tau is between 0 and t, then we are in this region. In this region, the purple one is 1 multiplied by the white one, which is still 1. It will become 1. And another region is when you have tau greater than t. We are here. The purple one is 1 multiplied by white one, which is 0. It will become 0. Yes, please.
So t is like a point.
It's
at
a
the-
shifting point. It's
Okay.
the amount of shift you do
Okay.
in this case.
Okay.
Yes,
What
please.
if you want to shift it the other way?
You can do that. If for any signal, let's look at here. This u of t minus t0 is shifting to the right. So t0 is positive, it comes here, okay? But assume t0 is negative value. It's like minus 5, and we have here. Then it will become u of t plus t0. Why? Because you have u of t minus t0 or minus 5 or minus 10, which minus times minus make it positive. And then you have a shifting to the left, and the plot would be, for instance, for unit step, it will become like this one.
That's the same thing with
Yeah.
T.
Sorry, what?
It's the same thing with the T. The T changes from minus to plus. That's why I said it should be mirrored on the other side.
T becomes positive, you're right.
Yeah.
But here you can see we have minus tau. But here I have,
Okay, yeah.
it's different. They are different from each other. I understand that it's a little bit confusing, but they are different. We cannot make the conclusion, the same conclusion for both. Okay. So now we obtain this. And why I did this, because in this equation, when I replaced f and g with the causal format, I had this here. This is what we plotted there, and we did a multiplication. So I want to use it, this one, and now multiply it by f of tau, g of t minus tau. So we go to report number 6. So now f of tau, g of t minus tau, then this is what we plotted here. So if I use this results here, again I use the same range. If tau is smaller than 0, tau between t of 0 and t. Okay. If tau is smaller than 0, we have the multiplication as a 0. So this is fg times 0. So this one becomes 0 as well. For this range, this part is 1. So it will become f of tau, g of t minus tau, multiplication by 1, and here is 0 again. You can use whatever I have in this bracket and write it here, or copy paste it in this slide. What is it here? They are empty here, but you can fill it out based on what I have on the board. So now let's back to this equation we had for convolution earlier. So f and g in a general case, the convolution is this format. But because in reality we work with the causal signals, I replaced f and g with the causal, and then the multiplication became this one, which is now in a simple form, this bracket, or this expression we have there. So what I do now, I can open this integration of minus infinity to infinity to these 3 intervals. If I do that, of course we have a summation of 3 different integrals. One from minus infinity to 0, one from 0 to t, and another one from t to infinity. The first one and the last one becomes 0. Why? 0 because of these 2 lines we have here. So the only term which remains is this one. So if you have 2 signals, which is mentioned, these 2 signals are causal signals. So they are in the format of multiplication with the unit step. So they are causal. Then the convolution integration from minus infinity to infinity can be replaced with this one only. So you do the integration only from the range of 0 to t of these 2 signals. So for general case, we have minus infinity to plus infinity integration. For causal signals, this is the integration. obtain the convolution of two signals. Any questions so far? Are you with me or you are lost on the way? Just let me know.
So will causal signals always be unit step functions in this course?
The causal signals are the signals which they have values on a positive range of t, which the easiest way to convert any signal to causal is if you multiply it by u, because u is 1, so practically the signal will remains the same because it operates in a positive time only. But yes, this is the easiest way to make any signal as a causal signal. Okay. Now I have example number 3, and I will solve this myself. We want to find the convolution of two u together. So this is example number 3. So u convolve of u of t. So I'm convolving two signals. And these two signals, both are u, and we know both of them are causal. Am I right? Because they have only values in a positive range of t. So I can use this formula of 0 to t part, not from minus infinity to infinity. So if I do that and follow the formula I have here, so the first one, the function f, it will become f of tau, which my f is u, so it will become u of tau. Again, the g is the same as u, so it will become u of t minus tau d tau. I need to solve this integration now. And some multiplication in between. Actually, we are very lucky here because what? Because we already found that this multiplication for the range of 0 to t is always 1. So what I can do here, I can replace it with the integration of 0 to t of 1 d tau. So if we do the integration, it will become, I think, tau for the range of 0 to t. So I put the upper limit first, minus when I put the lower limit. So the answer would be t. But this one is an easy one because we know this can be replaced by 1. But in exercises you have for later today, you will do it a little bit difficult ones. Now let's talk about some properties of convolutions. This convolution operation is commutative. So what does it mean? It means that if you convolve f and g together, f convolve of g, the result would be always and always the same as if you convolve g with f. So we call it commutative. Commutative. It's also associative operation. So what does it mean? It means that if you convolve f with the result of this convolution, it's the same as if you convolve f and g first and then convolve it with h. And then the convolution of f with direct delta function, or the convolution of direct delta with any function, would be the function always, it would be the function itself always. This one is very important to remember and use it. And also we can say the convolution is distributive. So f convolved of g plus h is the same as if you convolve f and g and convolve f and h and then add them together. These are some properties which it's good to know and use them. Now, Laplace transformation of convolution. Assume you have signal f and signal g, which we can obtain, or we have the Laplace of each, capital F and capital G. Either you can find them, or you can, it's given to you. If you convolve f and g, and you want to find the Laplace of those, actually this property is very important, and you will see it a lot in digital signal handling course as well. So the Laplace of convolution in time would be always and always the multiplication of each individual in frequency. So convolution in time becomes multiplication in frequency. This is very important one. And actually, I don't have an exact formula here, but if you have a multiplication in time, it will become convolution in frequencies again as well. So if I want to write it, I will check the exact formula, but if I have f t times g of t, and then we type Laplace, it will become f convolved of g in s, and I think we should have some normalization factor here as well. I think it should be 1 over something. I will check the exact formula, but the convolution in time is multiplication in frequency, and then we can say that the multiplication in time also becomes convolution in frequency. I will check if I can find this normalization factor. Find it and put it in there later. Okay. Now, something which is good to know or remember is that if you remember, we know that the output in frequency is always the multiplication of transfer function with the Laplace of input. You used this before to find the output in time. But you can see that I can take the inverse Laplace from what I have here, and if I obtain the inverse Laplace from both sides, I have the inverse Laplace of y of s, which is y of t. Then we have inverse Laplace of this multiplication in frequency. And the multiplication in frequency will become convolution in time. So from here, we can say that if you convolve h, which is the impulse response, again, if you remember, h, small h was always impulse response. So the convolution of impulse response with x in time will give you the output in time as well. So instead of doing the inverse Laplace and so on, another way to find the output in time is to use this formula. We have an example, which we will do it together. So this differential equation is given. We want to find the transfer function first, then obtain the impulse response. So we want to find small h. And then by using the convolution, we want to find the output of the signal when the input x of t is this expression which is here. Let's do it together now. So we need to find the transfer function. This is example number 4. So I need to take the Laplace, and then Laplace of output over input is a transfer function. So if I do that, I have s2 y of s. And with the zero initial condition, so 2 times y of s plus
It's
t.
just
Isn't it just one s instead of
not
2
s.
to the power?
before.
Yes, yeah.
First
It is, it is the first derivative, sorry. You're right. Then 1 over s, y of s. Again, we use tables for this step. I can make the factorization now. So again, I multiply everything by 1 over xs. S plus 2. Which from here, ys over x of s, which is our transfer function, would be 1 plus 1 over s divided by s plus 2 plus 5s. So first I try to simplify the function as much as I can or rewrite it. So I make this as one rational function. So it will become s plus 1 over s. And I do the same here. Is it clear how I moved from the middle to the right part? What I tried to do is make this as one rational function and make this summation as one rational function as well. So in order to add them together, I made or rewrite them in a way that I pick all terms have the same denominator. So if I multiply by s and divide it by s, then they have the same denominator here. Then I can add it or write it in this way. S plus 1 all divided by s. We do the same here, and this is what we get. This one can also be written as s times s plus 1. Why? Because we always multiply those who are far from each other the transfer function. Any questions so far? Please take a picture of these two boards if you want. Then I will go and continue there.
You just pull board number 8 down just a little.
You'll switch.
Yes. Okay. So now we are done with part 1. For part 2, we need to obtain impulse response. We need to obtain small h. How we can do that? Any idea? Any suggestion? So now I want to obtain h of t. Yes, please.
Take the inverse.
Exactly. So h of t is always the inverse Laplace of h of s. And we obtain h of s. It's there. So I want to obtain the inverse Laplace of s plus 1 over s2 plus 2s plus 5. This function, as it is written here in this specific format, we don't have this in a table. However, with a small change, we can have something which is in a table. How? This can be written as s plus 1 over s plus 1 to the power of 2, which is s2 plus 2s plus 1 plus 2 to the power of 2. This is exactly the same as what we have here. And this is the format we have in a table, so we don't need to do partial fraction expansion anymore, so it's good. And from here, directly from table, we can obtain h of t, which it would be e to the power of minus t cosine of 2t times u of t. Any question for impulse response for point number 2? Okay. So for the last part, it says that use convolution and find output. So again, we had a formula for it. It is here. I have to use the last line here, which is said that y of t is the convolution of h by x in time. H, I have it from here. And this one, x, is also given. It's stated in the problem here. E to the power of minus du of t. So I will use this. H, as you can see, is a causal function, and x, which is also given, is a causal. So I can write this as an integration of 0 to t only. The first one is h, so I write as e of, and then it should become, again, based on the formula, if you remember, I write it here. It is f of tau, g of t minus tau, d tau. This is the general formula, so I'm using this one for convolution. So f of t should become f of tau, so it will become e to the power of minus tau cosine of 2 tau. Then write it for now, u tau. Then multiply by x, which is e to the power of, what was it? Minus t. So minus t minus tau, u of t minus tau, d tau. Okay. So far I just used the formula and nothing else. But let's look at u of tau. Can you remember from, do I have it here? Okay, I have it, u of tau in a pink color up there. For the range of 0 to t, what is u of tau? Yes, please?
1.
Exactly. So I can remove it because it's a multiplication by 1. What is, again, it's not there, but what is the u of t minus tau for the range of 0 to t? It still is 1, exactly. So again, we don't need to write this anymore. So let's solve this integration now. It will become the integral of 0 to t. I have the multiplication of two exponential, so I can write it as, or something else before that one. I write as e of minus tau cosine of 2 tau. For this one, I can write it as e of minus t times e of plus tau d tau. I just write this as a multiplication of two exponential terms. Are you already agreed? We can do that always. Now, this integration, it is with respect to tau, as you can see. But here I have a term, e to the power of minus t, which is not depend on tau at all. So when we have this type of situation, so we have a term which is not dependent on your integration variable, you can bring it out of integration. So I can write it as a e to the power of minus t. Now, integration of 0 to t of e to the power of minus tau cosine of 2t e to the power of plus tau d tau. Okay. Again, I can keep this as it is. No, it's t. Now,
Sorry.
yes, please.
The last part, cosinus of 2.
2 tau.
Yeah.
Yeah, thank you. Thank you. Perfect. Here, I have a multiplication of two exponential. So I can write this as cosine of 2 tau, then e to the power of minus tau plus tau d tau. And this is 0, e to the power of 0 is 1, so I can replace it by 1. And now it is integration of cosine only, which again, if you know, you can do it yourself, or if you can't remember, have an integration table on your computer so you can use it. So if we do the integration table, it will become 1 over 2 sine of 2 tau, and I should find it for the range of 0 to t. Now we go to the second, next four. Is it board number 8? So this one is 9. So it would become equals to e to the power of minus t. First, I put the upper limit there, so half of sine of 2t minus half of sine of 0. And what is the sine of 0? Yes, exactly. So this terms goes out, so it will become e to the power of minus t, or half, I can put it here, sine of 2t. And this is the outcome by using the convolution technique. Yes, please.
So by using this convolution technique, we always eliminate tau variable.
We don't eliminate, we obtain the integration with respect to tau.
Yeah.
And when we do the integration with respect to some specific variable, at the end, the result would be depending on the interval you have and not the integration variable. So we don't eliminate tau, we just solve the integration. This is how the integration works. Again, if you don't remember, just refresh your mind all these integration techniques. And I think we have the solution all here as well. Yeah. So it's also in the slides. Any question for this example? Okay. This is the last example for today, and we will not solve it here together, but I want to show it to you because this is one sample for actual exam question in the Laplace area. So let's look at it together, and if any part is not clear and maybe you don't know how it should be done, just ask. So it says that we have a linear time variant system, which we can represent it by this differential equation. And it says that x is your input signal and y is your output. And the system is at rest for t smaller than 0. So what does it mean when the system is at rest? Yes, please?
0?
Yeah, it is 0. So it only operates at the positive range of time.
Yeah.
So then you need to define the transfer function first. I think hopefully all of you know how it should be done by now. If you don't know, just ask me in the exercise sessions or later. Then determine or find the poles and zeros of the system, plot the pole zero diagram, and then analyze if the system is stable or not. And again, hopefully you know how to do that. Good. Then determine the system impulse response. So it's very similar to part 2 of this example we did. And the last part, it says determine the output signal when the input is this expression and when u of t is the Heaviside unit step function. And for this particular part, you can use Maple. So, any question for this example? Yes, please?
The function we got there, right? At 1/2 times e to minus t.
This is the output,
Yes.
yeah.
But the t inside the parentheses is like, it's the shifting value. It's not a variable, right?
No, it is t itself. We don't have
Okay.
any shifting here.
Okay. But we obtained it by putting the upper limit of the
Yes.
integral.
Yes.
But that is also a variable, or what?
This is the upper limit of this integration variable.
Yeah.
So when you put it there, but this t, for instance, assume the t is 10, then it will become sine of 20.
Yeah, so it's not a function we have there, it's a number.
If this is a function with respect to t.
Okay.
But if you have a specific value of for it, because sometimes we do the integration for the range of, I don't know, 1 to 2, then the upper limit is not t anymore. So this will become as a number if we do a plot-wise sketch. Yeah. But now your output is a function of time, and t is your x-axis. Yes, please.
The last question, we have to find the output signal. We're still operating in the time limit, right?
Yes. You need to find the y of t here. Exactly. And because your input is also, so you need to find the output in time. When the input is in time, is this expression, yeah. So, if you look at the previous exam sets, in the last 4 years exams, which I designed the exam questions, we had typically 2 exam questions on Laplace. One of them is something like what you see here. And another one is the one I told you, I think, in lecture number 2. Can you remember what was that? Piecewise functions, yeah. When you want to write it as a Heaviside function first, and then take the Laplace from it. So if you want to have a good grade in the Laplace, try these 2 sets a lot, because at least one of them in the exam, so you are ready for them. And if you do it as much as you can, you will become better on it. I promise you. Now, if you don't have any question, we can go to the exercise room. I will be there, but I have to leave at 11:50 because I have a meeting at 12.